This is 2019 AMC 10A Problem 21. A sphere with center O has radius 6. A triangle with sides of length 15, 15, and 24 is situated in space so that each of its sides is tangent to the sphere. What is the distance between O and the plane determined by the triangle? And there are A, B, C, D, E, 5 options. To solve this problem, we have to first draw the diagram. And I've already drawn a 3D version of this diagram, so let's just take a look at this for a second. So this is a sphere, and it has a radius of 6 here. That's the radius. Then the triangle is it's over here. So just imagine it's like a triangle that cuts through the sphere, and when it cuts through the sphere, it produces this circle, which is inscribed to the triangle. So this graph isn't that accurate, but the circle is supposed to be inside the triangle. So if I draw, having a 3D view isn't enough. So let's just draw a 2D view right here. So a 2D view would be having an isosceles triangle. So we have an isosceles triangle, 15, 15, 24, like that. And then, basically, there's a circle that's inside this triangle. So, a circle that's inside this triangle. So it's probably like this, and so that's the circle. So one thing we notice about this problem is that we want the distance between O and the plane determined by the triangle. So the distance is this thing that I drew in blue. This is the distance. Just imagine that this point is the center of the circle here, and then this line is perpendicular to this big circle and also the small circle. So first let's look at this graph from this perspective over here. See what we can figure out. Because essentially, if we can figure out the radius of this circle over here, maybe you can use certain properties like similar properties, or I don't know, circle properties, because this is essentially, so we can use this another circle over here to solve this problem. Maybe we could do that, who knows, but figuring out the radius seems like an inevitable step in this problem. So let's do so. So I'm going to draw the center of the circle. So we notice that this circle is the circle that's inscribed inside the triangle. It's the circle, it's an incircle. So what does this mean? Every triangle only has one incircle, and the incircle is the center of the incircle is where all the angle bisectors of this triangle meet. So like that. These are all angle bisectors. And furthermore, you realize they're it's externally tangent to the sides, meaning that it's equidistant from each side. So this is R, this is R, this is R, and this also is R. So which R did we want to use to figure out? Well, clearly we should use this R because this is a line, as this is an isosceles triangle. Being in an isosceles triangle gives you an advantage, which is that as long as I know that this line is the angle bisector, then as long as I know that this line is an angle bisector, which it clearly is, or this line, and I know that this part is the altitude, so this is the altitude, I know that in an isosceles triangle, the angle bisector and altitude is on the same line, and also the median. So this is one line because it contains the altitude, angle bisector, and median. This also means that this is 12 and this is 12. How do we figure out this then, the blue line? I'll call that h. H is going to be equal to, so we use the Pythagorean theorem, root 15 squared minus 12 squared, which gives us 9. So h is 9. So how does that help? Now we can figure out the area using h equals 9. So the area of this triangle is going to be equals to 1/2 base times height. Base is 24. 1/2 base is 12. Base times 1/2 base times height is 12 times 9, which is 108. What is that equal to? That's equal to the radius, the in radius, which is just the radius of the in circle, the in radius r, which is what we want to figure out, times the semi-perimeter. The semi-perimeter is basically the perimeter of the circle divided, the perimeter of this triangle divided by 2. The perimeter of the circle is, of this triangle is 15 plus 15 plus 24, which is 54. The semi-perimeter is therefore 54 over 2, which is 27. So if we divide both sides by 27, r is equal to 4. So that's actually a really good thing because r is an integer. So we're probably on the right track. So if we go back to this diagram, we can label r equals 4. So we have two lengths now, 4 and 6. How do we look at this problem? Well, we can look at it from the front view. So from the front view, we need a circle. From the front view, we need another circle. And for the circle, we're only going to look at the top half of it, because that's where all the action takes place. There's nothing on the bottom half of the circle. But what happens is, if we look at it from the 2D perspective of the front view, this is going to be the center, and then this is going to be 6. So the radius of the circle is going to be 6. Right? And then somewhere at the top, along this line from the really top point of the circle, so this is also 6, somewhere along this line, let's say this point, let's say from this point and to the side of this, to the circle, and we know that these two sides are parallel because this is 90 and this is 90 and that is 90, because they're both in the same they're both circles within a sphere. So this is gonna be 4, right? So if that's 4, and we want to figure out this blue line here, the distance, we want to figure out d, maybe we can use some properties of the circle. So let's connect the points together first. We know this is d, we know that is d, and that is 6 minus d, right? And we also know if we connect this line, that's 6. Like, it's kind of obvious, that's just the radius. So, having what we have, we can use the Pythagorean theorem because this is a right angle. So we know that d squared is equal to root 6 squared minus 4 squared, which is root 20. Sorry, I mean, d is equal to root 6 squared minus 4 squared, which is root 20. So d is equal to 2 root 5. And that is the answer to this problem, which is indeed d. So answer choice D. So thanks for watching. Bye.